Okay, so again we can go from Cartesian coordinates to polar coordinates here. This is the conversion. Or if we want to go from polar coordinates back to Cartesian coordinates, we have this. Okay? Alright, so we want to write the Schrodinger equation in polar coordinates, and since the Schrodinger equation involves the Laplace operator, that is del squared, which is defined to be del dot del, or the and which is d squared, partial differential with respect to x, second order differential with respect to x, d squared by dy squared, d squared by dz squared. So we need to learn how to take derivatives in spherical coordinates. Okay, so so we need to start with something. So the easiest thing to start with is to think about a small displacement in the position of a, imagine we have, again we've defined some point in space like this one here, and we have some, I should say that the r vector is the vector which goes from the origin to the point. Okay, and so if we imagine that we displace, that we move to a slightly different position, okay, then we have a differential displacement dr. Okay, and since the r vector, the displacement vector r, the position vector, is equal to r times r hat, okay, a distance times a direction, then if we take the differential of this, we have dr times r hat plus r times dr hat. Dr times r hat, these are already in polar coordinates. Okay, we just have r and r hat, but to get the differential dr hat, we need to take the partial derivative of r hat with respect to r times dr plus the partial derivative of r hat with respect to theta times d theta plus the partial derivative of r hat with respect to phi times d phi. Okay, and so in order to actually calculate this small displacement vector, we need to calculate these partial derivatives dr hat dr, dr hat d theta, and dr hat d phi. Okay. Okay, so in order to do that, we first should write the expressions for r hat, which is clear that we're going to need that, and it's not as clear, but we'll need theta hat and phi hat, and for completeness we should do those anyway. Okay, so if we write down the displacement, or the position vector r, which is equal to x hat plus y hat plus z hat, and then if we plug in the expressions in polar coordinates for x, y, and z, we get r sine theta cosine phi x hat plus sine theta sine phi y hat plus r cosine theta z hat. Okay, now one way to a simple sort of systematic way to determine the a unit vector is to, for example, the r hat vector is to take the partial derivative of r, the position vector, with respect to the distance r. Okay, and that'll give us a vector in the direction, and generally speaking, the direction of r, and then if we divide by the magnitude of that, then we'll get a unit vector. And the same thing for theta and phi, theta hat and phi hat. We take the partial derivative of the position vector r with respect to theta, divide by the magnitude of that, and same thing for phi hat, the partial derivative of the position vector with respect to phi, and then take the divided by the magnitude of that. So if we do those just systematically on this expression for r, then we'll get r hat, theta hat, and phi hat.